Swayam Prabha. Digital India. Educated India.
Hello, welcome to this lecture of the course Elements of Mechanical Vibration. The previous lecture deliberated different damping models, and in today's lecture we will devote some time to energy methods of deriving the governing equation of motion. So, if you remember the steps in carrying out vibration analysis on any mechanical system involves first converting the system from the physical system to a simplified vibratory model, and from that simplified vibratory model, like a spring mass dashpot system, we derive governing equations of motion by using Newtonian approach. That by default or the most convenient way, because we know how to get a free body diagram, identify what are the interaction forces, and then apply Newton's second law. So, that method is straightforward and works well most of the times, but it also has some limitations. When the system becomes complex, it is hard to keep track of the sense of the forces which are acting on the free bodies. So, an alternate and more elegant method, so to say, is energy method, where we make use of the energies in the vibratory system to get the governing equations of motion. So, we shall now focus on few alternatives that we have, but I mean these alternatives are a part of energy based methods. So, the first approach is, of course, once we identify the total kinetic energy and the total potential energy of the system, one way to arrive at the governing equation of motion is the average energy principle, wherein the average kinetic energy and average potential energy of a vibratory system is equated, and for an oscillating system this applies, that average kinetic energy is equal to average potential energy. You can imagine a simple oscillating pendulum. You can find out what is the average kinetic energy of the pendulum in a cycle and what is the average potential energy. If you equate it, you will get the governing equation of motion. The other method is principle of conservation of energy, wherein the total energy is of the system is constant, or alternatively put, if you take the the derivative, time derivative of the total energy of the system, that is equal to 0. So, either you write as T plus V is equal to constant, or the time derivative is 0. Once you write this equation, by the solution of this equation will lead you to the governing equation of motion. The other method, which is in a way similar to the first one, is to equate the kinetic maximum kinetic energy and maximum potential energy. And the last among all these energy based methods, which is much more comprehensively used and is most elegant one, is applying Lagrange's equation once we have again identified the expressions for the total kinetic energy and total potential energy of the system. So, the Lagrange's equation, if it is derived, looks like this. So, it involves derivatives with respect to the generalized coordinates. For a single degree of freedom system, of course, the equation becomes very simple, in that there will be only one degree of freedom. So, only one generalized coordinate may be x. So, dou t of dou t over dou x, dou t of dou x minus dou t over dou x plus dou v by dou x is equal to 0. So, that becomes the Lagrange's equation, and if you take these derivatives, finally you will get the governing equation of motion. So, we shall of course apply one or two of these equations in some simple examples to get the governing equation of motion for a vibratory system. As the number of degrees of freedom increases, most of us find it convenient to apply the Lagrange's equation, and then you can get as many number of governing equations as there are number of degrees of freedom or these coordinates denoted by I in this equation. So, with this background, let us look at how we can apply these equations of these energy methods to get the governing equation. Okay, now let us take an example of application of this energy methods. So, the example here is that of a vertical bar of mass m. So, a uniform rod of mass m and length L. Okay. This bar is connected to two springs at these locations. So, location A and location B, these are the two springs which are keeping the rod vertically straight. Okay. Now, what we want to do is to look at its dynamics once it is disturbed from its equilibrium vertical position. Okay. Now, just although we are going to implement the energy method to explore the governing equation of motion and subsequent expression for the natural frequency, just for the sake of comparison, I would like to quickly analyze this problem using the conventional method of Newton's application of Newton's second law. So, we all know that it would pertain to getting the forces located on this bar as a free body. So, the moment this bar moves about the fulcrum here at the base, so this is the fulcrum, the hinge about which the bar is expected to rock. So, the moment you have a small angular displacement theta about the mean equilibrium position, which is vertical assumed here, the restoring forces quickly act on this particular bar, and this restoring force obviously is going to be the stretch in the spring. That stretch is obviously going to be L2 into theta, because that is the length at which the spring is located. So, the stretch with the angle theta made is going to be L1 theta, and the restoring force then obviously will have to be K into this is going to be L2 theta, and this spring is going to get compressed, this spring is going to get stretched for clockwise theta motion, and therefore, at this point of connection at point B, the restoring force is going to be again in this direction, because this compressed spring is going to restore the bar to the equilibrium position, and then the restoring force is going to be K into L1 theta. That is quite straightforward. So, if you now apply the Newton's second law, the summation of all the moments about O, which is this point, is the inertia times the angular acceleration. So, theta and theta dot are assumed clockwise positive. Now, obviously, I can write this as I theta double dot equal to summation of all the moments are now going to be k into L2 theta times L2, that is the arm length, and then to that I would add the second moment due to the this particular spring. So, that is going to be k into L1 theta into L. Okay. However, it is obvious that if the bars rotates like this, there is going to be the gravity which is going to also jump in the set of forces and moments. So, what we assume that the bar being uniform, the total mass can be assumed here at the center of this total length, and then this mass or the gravity mg is going to act at the center, and this arm length for this arm length for the moment of the gravity force is going to be now negative, because these moments are all become or are going to be negative, and then the gravity is going to generate a positive moment, right, because theta is assumed positive this side. So, the moments in the direction of the angular acceleration are on the right hand side going to be positive. So, plus mg into the into this length, right. This is the distance at which the mg force is going to generate a moment. So, that distance obviously is L by 2, because L is the total length of the bar, L by 2 times sin theta. Okay. This is going to be sin theta, which I can approximate as theta for small angular displacement, and this is all the time we therefore have to use the assumption of small amplitude vibration, so that these equations are valid. So, if I write this equation that I am getting from the application of the second law, I can write this as I theta double dot plus k into L1 square plus L2 square into theta, and then of course, I will have to write this as minus mg L by 2 into theta is equal to 0. So, this actually is now my governing equation of motion. Here the gravity is accounted for, because the rod is assumed vertical. If it is assumed horizontal, so that the bar swings in the horizontal plane, then the gravity will not play any role in the moments generated trying to restore the original equilibrium position. Only the springs will come into action, and then the natural frequency obviously in the if the rod is assumed horizontal and the motion is in the horizontal plane, then of course the natural frequency will be k L1 square plus L2 square divided by the mass moment of inertia of the bar. Now, the mass moment of inertia which about this end of the bar can be written as ml square by 3, and if m is the mass of the entire bar, L is the total length of the bar, where L1 and L2 are the connection points, the positions of the connection point with respect to hinge. So, if we take the motion in the horizontal plane without gravity appearing or effective, then this is the expression, but in the presence of gravity, this additional term will be included in the numerator. Okay. This is basically the quick approach of getting the natural frequency using Newton's law. Let us focus on the energy method. So, as we discussed, the energy method will involve you first finding out the expressions for the kinetic energy and expression of the potential energy. So, the kinetic energy of various elements in the vibratory system, if we want to know, obviously the springs are assumed massless. So, the first assumption here we will make is that the springs, both this one and this one, they are massless. Okay. You can include the mass of the springs, and then of course, the expression will change, but we will take another example later to bring in the mass of the springs into the governing equation. But here let us assume the springs massless, and then the natural but then the kinetic energy expression is based on the kinetic energy stored in the motion of the uniform rod. So, that obviously is going to be half mass moment of inertia velocity, in this case theta dot whole square, that basically is your kinetic energy expression for the rod. And the springs are meant to only store the strain energy. So, the expression for the potential energy, in this case it is going to be strain energy stored, and that let us keep taking. So, the expression for the potential energy V is going to be the energy stored in the first spring. So, maybe this is your okay, this is the first spring at the top, let us say K, and you know the strain energy stored in the stretched spring is half K x square, where x is the strain in the spring. So, in this case the strain or elongation in the string in the spring is L2 into theta, that is our extension in the spring which is here located at L2 distance from the hinge. So, square of this basically is the strain energy of the first spring. The strain energy similarly of the second spring is going to be So, the strain energy of the second spring is K into L1 theta whole square. Okay. But again if we assume the rod to be vertically oriented, then in that case as the rod oscillates or leaves its equilibrium position, then the original energy, potential energy will also get reduced, because the center of mass is going to shift a bit. Okay. So, what we are saying here is that if this uniform rod let us say changes its position here. So, if this bar now changes its position from the vertical position, I am going to basically show the change in its center of gravity point. So, this gets shifted by this angle, and the drop in its position vertically is going to be for a small angle theta motion here, and then of course, this will be L by 2. Okay. See, the position of the center of mass is L by 2. This is going to be L by 2 minus L by 2 cos theta, is not it. So, this distance is going to be L by 2 cos theta, and the drop in the position is going to be L by 2 into 1 minus cos theta. So, the drop here is minus mg L by 2 1 minus cos theta. Okay. And how do I write 1 minus cos theta for small angle approximation? 1 minus sine square theta raised to power half, and then I can expand this and approximate this as 1 minus half theta square. We know that through ignoring higher order terms, and then of course, this finally turns out to be half theta square. 1 minus cos theta is approximated by half theta square. This approximation is of course valid for small angle theta. And then I can rewrite this as half k L2 theta square, or maybe I can write this as okay, I can write this as half k L1 square plus L2 square and theta square minus mg L by 4 theta square, because 1 minus cos theta is replaced with half theta square. So, this is your potential and energy expression, and now if I want to apply energy method, one obvious option that I have is that through conservation of energy I can simply write the total energy remains constant, which is the another way of writing it is ddt of V plus T, or total energy, is equal to 0. So, you can find out the relevant expression using this approach, but I can also use another alternative, and a more elegant and more commonly used approach is to apply or use Lagrange's equation. Now, the Lagrange's equation that we wrote in the previous slide read like this: dou t of dou t by dou q I dot minus dou t dou q I plus dou v by dou q I equal to 0. Now, this in this equation q I is basically the generalized coordinate. Now, in our case this generalized coordinate is theta, and therefore, this equation would read dou t of dou t over dou theta dot minus dou t over dou theta plus dou v by okay. Now, in our case this equation would reduce to, because there is only one generalized coordinate, that is theta, I can write this as dt by dt by d theta dot minus so I can write this equation because theta is the only coordinate in question. So, this is going to be dt by d theta dot minus dt d theta plus dv by d theta equal to 0. Now, if you take or substitute these expressions, we have this expression for the kinetic energy and this expression for the potential energy, then I can write let us take the first term, that is going to be d dt of derivative of this with respect to theta dot is going to be just I theta dot, and minus this term. Obviously, if you take the derivative of the kinetic energy with respect to theta, it is going to be 0, and then plus dv by d theta is going to be k L1 square plus L2 square theta minus mg L by 4 mg L by 2 theta. Okay, that is the expression we have equal to 0. Now, further I can write this as I theta double dot as the derivative with respect to time plus this expression of k L1 square plus L2 square minus mg L by 2 theta equal to 0, and that gives me, this is in our standard form, that mx double dot plus kx equal to 0. This one is in the similar form, and the natural frequency of angular vibration or angular oscillations is now going to be k L1 square plus L2 square minus mg L over 2, and of course, I can write I here, okay, and that would be similar to this expression that I got using the Newton's law, okay, and we expected to get the same expression irrespective of the method of getting the governing equation and the natural frequency. So, this is the governing equation of motion, and the natural frequency is obtained as you see here. Things are fine, and there are some interesting things that we can obtain from here. Maybe if you want to use the second approach of d dt of v plus t equal to 0, I can take the derivative of all of them. So, v plus t, and then in that case what I get is k L1 square plus L2 square, or let me write them with a different. So, this gives us what k L1 square plus L2 square theta dot minus mg L over 2 theta dot plus I theta dot theta double dot, okay, equal to 0, which ultimately gives me the expression. So, what happens is theta dot cancels out throughout, and I am left with the equation I theta double dot plus k L1 square plus L2 square minus mg L by 2 equal to, sorry, this whole bracket is multiplied by theta equal to 0, which actually gives me, comparing with the standard form of the equation of motion, omega n is equal to square root of k L1 square plus L2 square minus mg L over 2 over I, okay. And in all of these equations, I can be replaced with ml square by 3, that is the value of the mass moment of inertia of a bar of mass m of length L about its end, okay. Okay. Now, as I said, this up to this point is fine, but there is an interesting thing that we should learn from this particular example is, although the expression for the natural frequency we have obtained is k L1 square plus L2 square minus mg L by 2 over I, which is now being replaced with ml square by 3, okay. Okay. Now, the expression in the of the natural frequency has the numerator, which is k L1 square plus L2 square minus mg L by 2. This numerator can in some case turn out to be 0, depending upon the value of k relative to the mass of the rod, okay. Just imagine that the springs are so floppy and so so light in the sense of its spring rate, that in comparison the mass of this bar is so large that if you disturb this slightly on either side, and if the springs do not provide reasonable restoring force, it is quite possible that the moment of the gravity acting on the bar will pull it continuously without going back to its mean equilibrium vertical position. Okay. So, let us look at those eventualities by looking at 2 or 3 possibilities. One possibility is that their relative values are such that this numerator is greater than 0, then there is no problem in the sense that the natural frequency will be some numerical value, and obviously the bar will keep on swinging back and forth under the action of the restoring forces and the inertia of the bar. Depending upon the relative values, what is going to happen is that the time period of this swinging motion about the mean vertical equilibrium position, that time period will change based on the relative values of k and the mass of the bar. Okay. But it will oscillate about this hinge, that is for sure. Okay. Let us look at what happens if the equation that we discussed, that is I theta double dot plus this entire bracketed term times theta equal to 0. Now, this bracketed term was basically the numerator here. Okay. So, now what we do is we take the case where k L1 square plus L2 square minus mg L over 2 is actually equal to 0, that is the threshold point. So, if this is greater than 0, this expression, then we know that it is going to be an oscillatory system, the system will have natural frequency as given by this, no problems for that. But there is one threshold point here, that if this term is equal to 0, that then what happens? Then basically what we get is I theta double dot equal to simply 0, right. So, the expression that we now need to solve, or the equation that we need to solve, is theta double dot equal to 0. Now, what is the solution of this expression? The equation can be solved by integrating. So, theta dot t is going to be let us say a constant C1, and then if you further integrate is and if you further integrate this becomes theta t equal to C1 t plus C2. These are two arbitrary constants, integration constants, and they can be obtained using initial conditions. Okay, at t is equal to 0, the initial conditions are theta at t is equal to 0 is theta naught, and at theta dot t is equal to 0 is theta naught dot. And now, if you substitute in these two initial conditions, theta naught dot is equal to C1 and theta naught from the second equation, which is this, you get this as C2, which actually then gives me the final expression of the response theta as a function of time t equal to C1, which is theta naught dot t plus C2, which is theta naught. Okay. That is our the final solution of this particular case, when the numerator actually is exactly equal to 0. With that condition, the response is this. Now, look at what this response tells us. Now, this response tells us that if our initial conditions are theta naught dot equal to 0, that means the initial velocity, I suddenly if this bar rod is standing straight vertically up, and then if I do not give any initial velocity to it, but I give some initial displacement, angular displacement to it, which is theta naught, which may be, let us say, if I disturb this and gradually tilt it by an angle theta naught, any angle, maybe let us say 10 degree, 20 degree, then in that case the response subsequently, after I displace this by an angle theta naught, the subsequent response theta t obviously is going to be just theta naught, which means that the bar will simply tilt and remain tilted at that point, at that position. Nothing will happen, neither will it oscillate nor will it continue to travel. That is going to be the equilibrium position. The bar is going to be in that equilibrium position forever after time t is equal to 0, right. However, if instead of giving any angular displacement to it initially, if I perturb it by giving some initial velocity, some initial angular velocity theta naught dot, that I just tap it with some initial velocity, and if that happens, then theta t is going to be omega t, which actually means that the subsequent angular displacement of this bar is going to continuously grow with time. Okay. It is going to rock, or it is going to swing continuously as t progresses. It will continuously go forward. It is going to rotate in the clockwise sense, depending upon, of course, in which direction the initial perturbation velocity I give it. So, which actually means that the springs are not good enough to bring it back to its original equilibrium position. So, the vertical rod is going to just fall like that, and it is not going to return, which is the condition that we always relate to in a simple vibratory system, that there is a continuous interchange between the kinetic energy and potential energy. The mass travels back and forth continuously moving about its mean equilibrium position. For this case, the mean equilibrium position assumed was vertical position. So, this is a case of a system that is getting unstable. It is not reverting to its original equilibrium position. So, the motion continuously grows with time. Let us take another the third case actually now in this case, wherein this k L1 square plus L2 square minus mg L by 2 is actually less than 0, which actually means that the numerator goes negative. Okay. So, in this case what happens, which actually means that the squared natural frequency is a negative quantity. You can see that if the numerator is negative, if I square this, omega n square is going to be a negative quantity. Okay. So, I assume this omega n square as, let us say, alpha square. Okay. And then what happens, I have the expression here as theta double dot minus alpha square theta equal to 0. Okay. So, just have a look at this particular expression that we have written as a general expression, which actually should have been, I mean, if I write this as theta double dot plus omega n square theta equal to 0. This is quite similar to the expression mx double dot plus kx equal to 0, then we can write this as x double dot plus omega n square x equal to 0. Now, in this case, this omega n square being a negative quantity, I am writing this expression, as this. Now, how do we solve this? We know that I can assume a solution of theta as let us say a e to the power s t, the root s, is assumed, and then obviously this theta double dot will give me s square a e to the power s t. We did this in this undamped vibration case earlier. So, now I can write this as s square, and you can show that this is going to be the equation that we would get, and which means that s is equal to plus minus alpha. Okay. And now if the two roots are given by these, S1 is plus alpha, maybe S2 is minus alpha. So, the general solution that I wrote here is theta t equal to a e to the power S1 t plus b e to the power S2 t, which actually means that a e to the power alpha t plus b e to the power minus alpha t. There are two roots, plus alpha and minus alpha. So, this is how the equation turns out to be. Now, usual things in the sense that I would like to get the expressions for a and b the way we do. This is done by implementing the initial condition. So, this is a alpha e to the power alpha t minus b alpha e to the power minus alpha t, and then these two equations substituting the initial conditions that at theta t equal to 0 is theta naught and theta dot t is equal to 0 is equal to theta naught dot. Okay. Then what happens is that I get the first equation gives me 0 equal to a plus b. Okay. This equation gives me a plus b equal to 0 because theta naught, and using this equation theta naught dot gives me a minus b into alpha. Okay. So, using these two equations we can get expressions for a and b. Obviously, a plus b is theta naught and a minus b is theta naught dot by alpha, right. So, let us say if I write this a minus b equal to theta naught dot by alpha, then if you add these two expressions we have a equal to half of theta naught minus theta naught dot by alpha, isn't it. So, oh sorry, this should be plus, and you can definitely substitute for a in this expression to get b, and then of course b is equal to b will be equal to a theta naught minus a, and a itself is half of theta naught plus theta naught dot by alpha, right. So, that gives me b equal to half of theta naught minus theta naught dot by alpha. Okay. As expected, that is how a and b would look like. And now I can write the final expression of theta t, which is equal to if I substitute for a and b, I can write this as half of theta naught plus theta naught dot by alpha e to the power alpha t, because a is with alpha t, and then plus half of theta naught minus theta naught dot by alpha e to the power minus alpha t. Okay. Now, what do you infer from the response expression that we have got? Theta t is nothing but your vibratory response as t progresses under the implied or input initial conditions of angular displacement at t is equal to 0 as theta naught and angular velocity initial angular velocity at t is equal to 0. So, once you give these two initial conditions, the response is given by this expression. Now, look at what the expression that we have got. Let us first figure out what do we infer from the second part of this expression. The second part tells us that no matter what theta naught and theta naught dot is, the multiplying function here e to the power minus alpha t, where alpha we have seen is a positive quantity, which means that this is exponentially decaying term, and as t progresses, this particular multiplying term is going to be reducing with time, and therefore, no matter what the amplitude here turns out to be, whether positive or negative, this response is going to become 0 as time progresses. So, there is no problem from the second term actually, but the first term here, so depending upon the value of initial displacement or initial velocity, even if one of them is there or both of them are there, the response is going to grow. Why? Because the multiplying quantity here is exponentially exponentially increasing. The multiplying term here as e to the power alpha t is having a positive multiplying component to the t, and then therefore, as t progresses, the exponentially increasing amplitude is going to be expected. So, which actually means that when this particular condition is satisfied, then you have an unstable vibratory response, right, unstable irrespective of what initial displacement or initial velocity is, which actually means here that if the rod is disturbed, it will continue to move as time progresses, right. So, therefore, this is the case of an unstable vibratory system, that the with whatever initial conditions that you give, theta naught or theta naught dot, the response is always going to be unstable response. Okay. This is the concept of stability in this particular context, even in case of the undamped vibratory system.